Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to talk about two things and their connection. Momentum and something called impulse. Now, in our last video, we learned that momentum is mass times the change in velocity. Now, impulse is related. Turns out momentum can actually mean something else too. So if you think about it, I'll just say it and then we'll talk about it. It also can be the average force times time. Now to sort of prove that, so force times times and mass times velocity are the same thing? Actually, yeah, they are. If you think about it for a moment, mass is kilograms, and that's meters per second. Now a force is mass times acceleration, so that's MAT, which, if you will, that'd be a kilogram meter per second squared times a second. This second cancels this second, kilogram meter per second. So this is this equation helps us to solve lots of interesting questions. So why is this important? Well, this is the principle of, say, an automobile crash, or if you're in some kind of a crash. The issue that's going to hurt somebody, honestly, is force. So for example, I know, or I looked it up, that let me back up before I say that. What would be the units on impulse? Impulse's units are going to be a Newton times the second, which is still the same as kilogram meters per second, but we call it a Newton second. And as a note, the symbol for impulse, it's kind of weird, I like to just use capital I, but technically it's a J. I have no idea what's a J, but we can also say that equals I. Okay, and this is a vector. So this is what impulse is, but why, what's the application? What's the important point on this? So I was getting to that. It turns out, you may not realize this, but if I wanted to crush a human skull, requires 2,300 newtons. That's the force to crush a skull. So imagine that you're in a car accident, you're moving at a particular velocity, a particular mass, and I want to minimize that force. I want that force to be as small as possible. What can I do? You know what the answer is time. All right, so I have brought with me my bicycle helmet, right? I got my bicycle helmet on. Why do we wear bicycle helmets? To protect our head. But how does it protect our head? You know what it does? It increases the time during the collision, which decreases the force, the average force. That's what it does. So let's take a problem. Let's say that we've Gav. I'll write it out here, and then you follow on. A 50-kilogram cyclist traveling at 9 meters per second has an accident and lands on his head. The helmet causes the force to be distributed over 0.2 seconds. Is his skull crushed? So if you think about this, we know the mass, we know the change in velocity, we don't know this, and we know the time. So I would say 50. So I'm just mv equals f times t. M is 50. The velocity, by the way, he's traveling at 9. The change in the velocity goes from 9 to 0. He crashes, right? So that's going to be times 9 equals f times 0.2. Right? You do the math, and I don't have my calculator with me. And I get a force equal to 250 newtons. Now, what causes someone to crush their skulls? 2,300. So this cyclist is probably going to be okay. Probably going to have a headache, but probably not going to die. So, and this is the same principle of in a car crash. You ever seen like an image like this where you've got the crumple zone? So the idea of a crumple zone is that it's going to cause the accident to last longer, and you're going to increase the time, back to the equation here, you're going to increase the time, which is going to reduce the average force, because what's going to hurt the human in the accident is the force. And ultimately, a lot of the problems you're going to work on when you're doing the homework are going to be problems like this. If you just understand, impulse is F delta T, units are Newton seconds, and momentum is m times delta V, which is a kilogram meter per second, but they're often equated to each other. Houston, we don't have a problem.